Yeah, so I hope you can hear me. So the first question is, which part of the electromagnetic spectrum has the longest wavelength? Option A, radio waves, option B, infrared radiation, and option C, ultraviolet light, and option D, gamma rays. So whoever knows the answer can raise your hand. You can take a couple of minutes. Yeah, Vishwajit.
Sir, right option or wrong option?
Right option, right option.
Sir, option A.
Okay, why do you think it's radio waves?
Uh, like,
Yeah, you can just justify why you would choose that.
because uh, infrared and ultraviolet ray are near to the visible light,
Mhm.
and I'm not sure about gamma rays.
Okay,
And radio waves are, those are, I think, electromagnetic waves.
all of these are electromagnetic. So this is a spectrum we have classified according to our purpose. So one way you can think about this is radio waves are used to communicate through long distances.
Yes.
The word radio itself should remind you of that. So in order to communicate through long distance, having longer wavelength would be beneficial.
Yes.
So that is one way you can think about this. So shown here is the is just a it is just an image where you see different classifications according to wavelength and what is the approximate frequency that these would take up. There is a relationship, inverse relationship between frequency and wavelength. So higher the frequency, lower the wavelength. Fine. This is a simple question just to start with. The next question is, yeah, Vishwajit, do you have any question?
Why I said radio waves, because don't mind, but uh, recently, that incident happened in Middle East.
Hmm.
Due to that, I I thought this would be the right option.
Yeah, you can communicate from one device to another device through long distances.
Yeah.
Yeah.
Answer one. One general question,
Yeah.
that when we look into sky,
Hmm.
then there is no green light. There is red, orange, yellow,
Hmm.
um, sometime purple and violet are also there, but there is no green light.
No, people have observed that as well.
Okay.
Even very recently, there was this one thing in the Europe where I think it's called Aurora Borealis, where you see this green light. You can maybe check that. All of these are so you need you if you see a particular color, that means Light waves are hitting onto something and reflecting a particular wavelength. That is how you need to understand. So
Okay.
when you hit light on leaves, they absorb every color other than green. So they reflect green. That is why you see
Okay.
the leaves as green. So in the
Okay.
atmosphere, if you have gases that can absorb energy of a particular wavelength and reflect energy of another particular wavelength, the color corresponding or the frequency, okay, or the frequency of the wavelength corresponding to the energy which is being reflected is what you will see.
Okay, sir.
Right. Hmm. The next question is UV visible spectroscopy is primarily used for option A, characterizing electronic transitions. Option B, measuring mass. Option C, analyzing atomic composition. Option D, determining molecular weight. We can take a couple of minutes and then start discussing. So for this question, maybe we can start by the elimination method. Whoever wants to answer can first eliminate a wrong answer, justifying why that option is incorrect. We can take a couple of minutes. Yeah, does anyone want to try answering? Ushajit, Rajata, Chandrima? Yeah, you can unmute.
Sir, option D, determining molecular weight.
Hmm. So, why do you think UV visible spectroscopy will not be useful for that?
Sir, it's not a function of UV visible spectroscopy, sir. Um, Techniques like mass spectrometry,
Hmm.
yeah, are commonly used to determine this.
Okay, right. So that way we can eliminate option B as well, is it?
Yes, sir.
Okay. Yeah, Chandrima.
So option C, analyzing atomic composition.
Hmm. Okay, why do you think it will not be beneficial, UV visible spectroscopy?
Sir, it doesn't tells about what is the atom's composition. what are the atoms are present in it. It is actually works in the IR spectroscopy where we know about that functional groups. What in the atom is what is that the bond using the vibration. So it is not the function of UV visible spectroscopy.
Hmm. Okay, so we agree that the function of UV with UV visible spectroscopy we can characterize electronic transitions, right?
Yes, sir.
So do you know why specifically UV visible spectroscopy is used for characterizing electronic transitions? Is there something very specific about the wavelength or the energy levels? Okay, I'll repeat myself. I was asking if there is something very specific about UV visible spectroscopy, such as the energy levels or the frequency levels, which is the reason behind its use in characterizing electronic transitions. Does anyone have any idea about this? You can unmute and tell me whatever you know about this.
Sir, actually, in UV regions, there are various parts like far UV region, near UV region, and vacuum UV region. That some like alkanes, the electronic transition, what is happening in sigma to sigma star,
Hmm.
that is very high energy process, and that frequency or that matches with that vacuum UV region.
Okay, so we agree that there is some energy that is needed for this electronic transition to happen, right? Which means
Yes.
that electrons at a particular energy level, they have to displace to a higher energy level or a lower energy level. And this would happen in this particular energy range, which is UV visible range. Like you mentioned, there are classifications near UV, far UV, and the visible. So, if you look at electronic transitions, one thing that you need to know is that this UV visible radiation it corresponds to only for outer electrons. Majorly, we've been studying the transitions involving pi, sigma, and n electrons. Pi is the one where you have double bonds being formed. Sigma is the one where you have single bonds being formed, and n is the lone pair of electrons. Okay. So when an atom or molecule could absorb energy, these electrons are promoted from the ground state to an excited state. By excited state, we mean that it's an uh, state where the energy levels are higher than the ground state. Now, these levels are discrete, meaning you need to have a specific uh, energy level, energy value. It is not a continuous value. And this is a typical representation of how the orbitals are present. You have bonding sigma orbital, bonding pi, then the non-bonding n, then the anti-bonding pi star, and the anti-bonding sigma star. So the energy required for the maximum transition, as you can see here, from sigma to sigma star. And you have respective other transitions as well. Now, what is observed is that sigma to sigma star transitions is not seen in they say that it's not seen in the UV visible spectra, but it has lesser wavelength at around 125 nanometers. But N to sigma star, which is here, is in the range of 150 to 250. So it's present in the UV region. And N to pi star and pi to pi star, these are present in the UV visible region. Now, owing to this reason that a specific wavelength matches the energy requirement for transition from one bonding orbital to another anti-bonding orbital, is the reason why UV visible spectroscopy can characterize these electronic transitions. Was this clear? Okay, I'll move to the next question. The next question is, in UV visible spectroscopy, the absorbance of an analyte is directly proportional to, four different options are given here: the temperature of the analyte, the concentration of the analyte, the wavelength of the incident light, the refractive index of the solvent. We can take a couple of minutes and start with how you would, what would you call as absorbance and how can you measure absorbance? And we'll try to have a better understanding of how this absorbance is determined based on the interaction. Does anyone want to try answering? So the question was, how would you measure absorbance? You pass light. Now, how would you measure absorbance? Do we have a reference to compare with? Does anyone know or have idea about this? Yeah, Chandrima.
Sir, generally, when we use the spectrophotometer, we used to do two cells. Like one is at the sample cell, and another one will be the reference cell. On
Okay.
the basis of that, they can vary that.
Okay. So what will your reference cell have?
Generally, sir, in the microbial count, it was actually when we are talking about that reference cell is uh, the like what we are doing, that should be the sample one, and the reference one it would be filled with a water or something. It's a fluidic substance, we have to fill it down.
Right.
Perfect.
Right. You're partially right. 1 minute, Vishwajit. So we'll talk about this with respect to proteins. So proteins are generally present in buffers. In that case, what do you think will be the reference, Chandrima?
In case of proteins, I
Hmm.
mean protein is present in the buffer.
Proteins are present in buffer. So in that case, what would the reference cell contain? You can take a minute, Chandrima. We'll listen to Vishwajit. Yeah, Vishwajit.
Sir, we will take this uh, um, DNS free, sorry, proteinase. No, we will take water. I mean, pure water. I don't. I mean, I am not uh, clear, but we usually take reference as water for blank.
Yeah, so your blank, what the reference is called as a blank, that is right. You need to decide what your reference is based on what your biomolecule is present in. If you dissolve your protein in water, then your reference cell would contain water. But usually proteins are present in buffers, which would ensure that the pH is maintained. So,
Uh,
in case of proteins or other biomolecules, even DNA, in some cases, people elute that in nucleus-free water. In other
yeah,
cases, they elute DNA or store DNA in tris EDTA solution, which is again a buffer and and it contains a chelating agent called EDTA.
yeah.
Right.
Okay.
Okay. Okay. So now we've discussed about the concept of blank. Now, why is the blank essential?
To measure the concentration of uh, uh, solute or an I mean particular molecule.
Let's say you have your biomolecule, you put that in your spectrophotometer, you will get an absorbance. Why can't you directly take that as the absorbance of your solute?
Sir, because um, we have to take as a blank as a zero.
Okay, I'll rephrase what you said. So, the reason behind we have the concept of blank is because these are also molecules containing carbon, hydrogen, nitrogen, and oxygen. So, they have the same kind of bonds, which could also absorb and give some absorbance. So you need absorbance specifically for your biomolecule. So in order to subtract that, you usually take your buffer without your biomolecule as your blank, get an absorbance, then take your biomolecule at different uh, concentrations maybe, then check the absorbance. and you subtract it to get the absolute concentration of your solute. Was that clear?
Yes, sir.
Okay. So is there any option that you can eliminate here?
Option A.
Temperature. So you think temperature wouldn't change the absorbance? Okay. Any other option?
Sir, another one is refractive index.
Hmm.
It is not at all related with that absorbance.
Okay. What is refractive index?
So it's a ratio between like sin I by sin R, the sine of
Okay.
angle of incidence and the sine of angle of refraction.
Hmm. Is there another way to talk about the refractive index? Okay, it's not clearly relevant. Okay, we'll skip that. What about the other two options? Does the wavelength of incident light determine, is the absorbance directly proportional to the wavelength of the incident light?
So the absorbance depends on wavelength,
Hmm.
but it is not directly proportional.
Right. So you have specific wavelengths where specific biomolecules could absorb maximally because of the electronic transitions, like we had previously discussed. Now, does anyone know what is the lambda max, which is the wavelength at which maximum absorption could happen for proteins and DNA?
So lambda max is actually that wavelength whose that molar absorption coefficient is maximum.
Huh. So if the molar absorptive coefficient is maximum, absorbance will be maximum, right?
Yes,
Yeah. So lambda max is the wavelength at which maximum light could be absorbed. That's right.
yes,
That's a way to say that, right?
yes.
Right. So do you know what lambda max is for proteins and DNA?
Sir, I don't know about that.
Okay, that's
For
not an
proteins,
issue.
it's
Hmm.
nearly 280 nanometer.
Right. And for DNA or nucleic acids, DNA, RNA?
I guess it's 260, I'm not sure, sir.
Yeah, it is 260 for nucleic acids and 280 for proteins. So we were able to eliminate the three options, which leaves us with option B, the concentration of the analyte. So we think that the absorbance of an analyte is directly proportional to the concentration of the analyte. So we have something called as the Beer-Lambert's law, which tries to correlate how absorbance is influenced by different factors. So before moving on to absorbance, we need to know what transmittance is. So you have a cell or a cuvette where your biomolecule is present and you pass light through it. Let's say you pass 100 units of light, your biomolecules would absorb few units, and whatever reaches the other side will not be 100. So, with transmittance, we will be able to get how much light was allowed to be passed. Now, absorbance is the inverse of transmittance. That's why you have it here this way. Now we'll go to the law that tries to mathematically relate the factors that would affect absorbance. So, Chandrima, you were mentioning something called as molar absorbance. What do you think molar absorbance is?
Sir, it's actually a coefficient, means from the Beer-Lambert's law.
Hmm,
What is it's a proportionality constant?
it's a proportionality constant. Okay, does it have something more rather than just being a proportionality constant? Is it
Yes,
inherent
sir.
to molecules? So this molar absorption coefficient, is it the same for all molecules?
It will be varying from one concentration. It would vary
No, it is not concentration dependent. So
wavelength dependent actually. At different wavelength, it is having different.
yeah, so you can imagine molar absorptivity or molar absorbance as the how much can light be absorbed given 1 mole of a compound. You have 1 mole of, let's say, a protein. Now, how much light can this 1 mole of protein absorb? Uh, that is the molar absorptivity. Now, the second thing that we need to discuss is the path length. So, your cuvette will come in different shapes and different sizes, and which means the distance your light travels inside the cuvette would be different. So, if we consider these two as cuvettes, the amount of distance or the length which your light would travel would vary. And if the length your light would travel varies, that would mean the number of molecules your light would encounter would also vary. Let's say your light travels here and it encounters 4 molecules. But if you increase the distance, the amount, the number of molecules that your light would encounter would also vary. And it's more or less proportional. If you increase the size of your cuvette, more your light would come into contact with more molecules, so there will be more absorption, which is why this path length is directly proportional. And the third one is the concentration of the sample, which is what we were looking at. So these three factors are directly proportional to or is directly correlated with the amount of absorbance that you would get. Was that clear? Okay, I'll go to the next question. Which type of atomic or molecular processes are typically measured using UV visible spectroscopy? Four different options are given here: electronic, rotational, nuclear, and vibrational transitions. Yeah, you can unmute and uh, specify which atomic or molecular process is right here.
Sir, option A, electronic transitions.
Right, as we discussed. So the next question is electron paramagnetic resonance spectroscopy uses option A radio frequency waves, option B infrared radiation, option C microwave, option D gamma rays. Uh, so if anyone knows the right answer, you can answer that. You can take a couple of minutes to think about this question. Does anyone want to try answering? Okay, so this method, electron paramagnetic resonance spectrum spectroscopy, is a method that makes use of the spin of electrons. So your electrons have two motions that happens simultaneously. The first is your electrons move around your nucleus. That is one rotation. The second is your electrons spin while they move around the nucleus. So there are two ways in which you can calculate the angular momentum. And for this you need very high frequency in order to study this. Only then that frequency will be in resonance with the frequency of your electron's spin. So that is why among these four options, the highest frequency, which is radio frequency, is the right answer. The next question is, which spectroscopy method among the following is suitable for identifying functional groups? Option A, rotational spectroscopy. Option B, nuclear spectroscopy. Option C, vibrational spectroscopy. Option D, electronic spectroscopy. We can take a couple of minutes and then um, you can start eliminating the incorrect options. Yeah, does anyone want to try? So the question is, which spectroscopy method is suitable for identifying functional groups? Yeah, Chandrika.
So we will start with the wrong option.
Yeah, you can eliminate an option and justify why you think that will not be helpful in identifying functional groups.
So like the option D, electronic spectroscopy,
You think that's a wrong option? Okay.
because this electronic spectroscopy is working in the UV region, and actually does the electronic transition. It checks the electronic transition, but it doesn't identify any functional group.
Okay, so what does electronic transition help us with?
So the electron transition somehow helps us with any particular compound, like that it is an alkane or alkene or alkyne. It's a particular class. It's not a functional group. It
No,
can classify.
I didn't get you. Can you repeat? You were saying that electronic spectroscopy will not allow you to distinguish between alkane, alkene, and alkyne. Is that what you were trying to say?
Yes, sir.
So how you can understand electronic spectroscopy is how much it can allow us with respect to quantifying transitions like we had earlier seen. So if you provide energy to molecule, there are transitions in the electronic levels which emits light. So this spectroscopy method is used to study the optical properties but nothing more. So we can eliminate that option. Okay. Does anyone else want to eliminate other options? Vishwajit, Rajata?
Sir, option A.
Rotational spectroscopy. What is it, Vishwajit?
Uh, I mean, it is. I guess it is in UV visible. Visible spectroscopy. It is used.
No, can you repeat it? Can you repeat?
It is used in visible spectroscopy.
No, no. So we earlier talked about electronic spectroscopy, where these electronic transitions are used to characterize optical properties of compounds. That is where this visible light plays a role. The energy provided by visible light plays a role. What is rotational spectroscopy?
No, sir. I have no idea.
Okay. So within a solution, if you provide energy, do you think molecules can rotate? They are free to move, right?
Yeah, they are free to move.
Can bonds rotate?
Yes, sir.
Yeah. So the
Phi psi bond.
the
In
spectroscopy that tries
peptide.
to characterize this would come under rotational. And
Oh,
yeah. So what about the other two options, nuclear and vibrational spectroscopy? Can any of these be used to identify functional groups?
sir.
So,
Option B. Okay.
Yeah, one of you can unmute. Whoever wants can unmute. Rajata or Vishwajit.
so option B, nuclear spectroscopy, it's like NMR. So it provides information about the environment of the specific nuclei in a molecule.
So with that, you can't characterize the functional groups, is it?
Yes, sir.
But you said you can characterize the environment around a particular nuclei. So is it possible to characterize if a particular functional group is present?
Sir, it will not give like direct insight to it. Some insights into functional groups is it gives, that's it.
Okay. And I have some idea about this, some insight that you were mentioning. So let's say there is a particular molecule, it makes a hydrogen bonding interaction with a particular functional group. This nuclear spectroscopy will be able to tell us at what conditions this hydrogen bond is present and at what conditions hydrogen bond is not present. That interaction could be characterized, but you can't get into the details of the specific functional groups that are present. Was that clear?
Yes, sir.
Okay, so then what is vibrational spectroscopy? Does anyone know? Okay, we'll start with this simple idea. Why would do molecules, can molecules vibrate?
Molecular bonds vibrate.
Okay. What is there any particular pattern to the vibration? Okay, I'll get into the details. So, let's say there are bonds. Let me draw this. You have a C, you have a H. Now, this is nothing but an electron cloud, right? A bond is nothing but an electron cloud. Now, this bond can be pulled towards.
Excuse me, sir, your voice is breaking.
Yeah, can you hear me now? Can you hear?
Yes, sir.
Yeah.
Yes, yes.
So you have a CH bond. Now this bond is nothing but an electron cloud, which means that the electrons can be pulled towards a particular direction. That would be called as the stretching movement. CH stretching. Whereas you have this and you have some other molecule here. Now there is an angle between these two electron clouds and the angle might vary. That would constitute the bending moment. Now this also can be induced in molecules if you give energy. Let's say you give a particular energy level, this stretching can be resonated with that, with which you will be able to identify whether this molecule is present or not. Similarly, we can apply the same, we can apply a particular wavelength for the bending as well. So these two are the kind of vibrational spectroscopies that are used to study or to detect functional groups. And you have specific values in terms of wave numbers, such as around 3000 centimeter inverse for CH stretch, and around 1470 centimeter inverse for CH bend, and so on, with which you can specifically determine functional groups. You will be able to distinguish alkanes, alkenes, and alkynes, like how Chandrima was mentioning. Now I was mentioning about these electron clouds. So if there is one bond, this is very easy to move the electron cloud. But when there are two bonds, it's degrees of freedom, meaning the ease with which these two bonds can be moved becomes trickier, which is why you have differences in the wavelength, or sorry, the wave number, which would characterize these uh, vibrational spectrum. So that is how you can differentiate between a C double bond C stretch or a C single bond C stretch or C H stretch. Was this clear? I'll go to the next question. The next question is a UV visible spectrophotometer can measure, and four different options are given here. Option A absorbance, option B hydrodynamic volume, option C fluorescence, and option D zeta potential. So, as we were discussing earlier, this UV visible spectrophotometer can measure absorbance. The next question is the dash of a spectrophotometer splits light into various wavelengths. Option A reference cell, option B photomultiplier tubes, option C monochromator, option D detector. We can take a couple of minutes and then uh, start with why should spectrophotometer split light into various wavelengths. We can start with that and then go on to the right answer. Okay. Yeah. So, does anyone have an answer in mind? Why should a spectrophotometer split light at the various wavelengths? We had discussed a particular concept earlier in this class today, something known as molar absorptivity, which would also depend on lambda max. So, can someone try to correlate these concepts and justify why spectrophotometers should split light into various wavelengths?
To observe a particular wavelength.
Okay, so you're saying that it should observe only a very specific wavelength. So you're saying that it should observe only very specific wavelength. So we should give it a very specific uh, wavelength. So we need to split the light. Is that what you're trying to say?
Yes, sir.
Right. So which among these parts do you guys think is the one that helps in splitting light into various wavelengths?
Option C.
Monochromator. What does it do?
I mean, it is. bulb. Uh, yeah, um, it is like bulb which pass a particular particular light, and there is one um, a mirror, not mirror, there is one glass due to which uh, uh, different kind of wavelengths are particular wavelength of light are passed.
Okay, so you have a light emitting source like a bulb which gives you the light, but light is a spectra, which means you will have all wavelengths coming in. Then you have a filter, that is the monochromator, which
Yeah.
allows only specific wavelengths to enter. Right. So we have a figure just to show that. So your monochromator allows very specific light wavelength to pass through your sample, because your sample can absorb maximally at one specific wavelength and not at all wavelengths.
Okay.
The next question is a hyperchromic shift is option A shift towards lower wavelength, option B shift in absorption intensity, option C decrease in absorption intensity, option D shift towards smaller wavelength. We can take a couple of minutes and then start uh, yeah, we can take a couple of minutes and then try to describe what the hyperchromic shift is. Okay. Yeah. Does anyone have an idea about what hyperchromic shift is?
Sir, somehow it is related with when any chromic substance is very high in that sample, or it is going very high chromophore it is present.
So, what is a chromophore, Chandrima?
Chromophore is that substance which imparts color. Means when we are using staining, that there are two type of substance, like one is chromophore and one is also chrome. So that chromophore is imparting color to that substance.
When you say it is imparting color, let's talk in terms of light. Does it reflect light? Does it absorb light? What is happening there?
It actually absorbs the light.
It absorbs light. Okay. So when you said when they ask for hyperchromic, what could it possibly mean? Does it absorb more light or does it absorb less light?
Somehow it is hyperchromic. So it is hyper means very high. So it is the more light is entering, means absorbed.
Yeah, that's how you define this. So hyperchromic shift is the one where you see an increase in the absorption intensity. Right. There are a few other terms that I thought will be beneficial here. And one more thing that I wanted to discuss with you guys here is with respect to biomolecules. So you mentioned about something called as chromophore. Now, what all properties do you think the chromophore ability to absorb would determine? Do you think there are some things like the environment of the chromophore or the interactions of the chromophore that would determine its absorption intensity?
Yes.
Okay. Um, in the next slide, I have an image where we will see something called as, in biomolecules, how this is relevant. So we can focus on this particular strand. So, in case of double-stranded DNA, what happens is your nucleotides interact, form hydrogen bond with each other. So the electronic transitions are reduced. Because these electronic transitions are reduced, the absorbance is of a value that is lesser than what the same DNA would have if it were single stranded. What you see as a red peak here having higher absorbance corresponds to your single stranded DNA. Whereas what you see as this black peak is your double stranded DNA. And this is owing to lack of this hydrogen bonding interaction. This is what I wanted to convey when I was asking about the environment. So in this environment, there is a lack of hydrogen bonding, whereas here there is hydrogen bonding, which reduces your electronic transitions. Was that clear?
Yes, sir.
Right. And one more thing is, like we have something called as hyperchromic, we have something called as hypochromic as well. In the case of hypochromic, you see reduced absorbance, like what you see here, the inverse case. And there are two more shifts. One is hypsochromic, one is bathochromic. This would mean the wavelength at which it maximally absorbs either gets shifted to a lower wavelength, which is the hypsochromic or the blue shifted, or higher wavelength, which is bathochromic or red shifted. Okay. The next question is, when an oxochrome is attached to a chromophore, what happens? It shifts to a longer wavelength, it shifts to shorter wavelength, it increases absorption intensity, and D, wavelength remains constant. We can take a couple of minutes and then start by describing what an oxochrome is. Then we'll go to chromophore. Yeah. Can anyone describe what an oxochrome is?
So actually, oxochrome is sort of some kind of functional groups that it gets attached to that chromophore, so it enhances that color or that intensity. It helps in that, like, to form any salt or to bind to that color or that stain to that fibers or tissue, whatever we are staining.
So, does it also alter the environment of your chromophore in some way?
Yes, when it is attached to an chromophore, it alters that chemical structure also.
So, the environment is changed, the structure is changed. So, now electronic transitions can happen, which will lead to which of these options? Does it shift to longer wavelength or shorter wavelength, or does it increase the absorption intensity, or does the wavelength remain constant? So we've discussed how the oxochrome could interact with the chromophore and affect it. But on a general basis, do we can we say how an oxochrome is changing the intensity or the wavelength? Is it possible?
So, but when oxochrome is attached to a chromophore, it helps to stabilize that chromophore. It helps to increase that absorption intensity.
Is that a necessary phenomenon, Chandrima? Because your oxochrome could your oxochrome interacts with your chromophore. This interaction could lead to increase in intensity also, decrease in intensity also. So, can you really say that an oxochrome is always helping in increasing the absorption intensity? It would be it would vary on a case to case basis, wouldn't it?
Yes, it would vary somehow. In
Right. So we can try. So there. So all the four options given here would be applicable on different cases. So this doesn't have one single correct option. Although in the prescribed text it is given as it shifts to longer wavelengths, this oxochrome, because it just changes the environment around your chromophore, it can do all the four. You won't unless you talk about a specific case, you can't really generalize this answer. Okay.
Sir, what is the answer?
So for this question, I would say there is no specific right answer. All the answers are right in specific context. You cannot generalize this, but your prescribed text says that it is option A.
Okay.
Right. The next question is dash stops the reformation of disulfide bonds. And four different options are given here. Dithiothiotol, which is DTT, beta mercaptanol, which is beta ME, perforic acid, and iodoacetate. So this is actually slightly incorrect. It's actually iodoacetamide. You can consider this as iodoacetamide instead of iodoacetate. Now we can take a couple of minutes
and start with the context. Where do disulfide bonds form or reform, and what is the kind of environment that is needed for this formation? Once we discuss that, we'll take it from there. Okay. Yeah, to start with, can anyone describe what is the context of disulfide bonds with respect to biomolecules?
So in disulfide bonds, it actually it happens when cysteine or methionine is are the sulfur containing amino acid. So when they bound to that, so there the disulfide bonds get created, or the cross linking of that many protein peptide chain is also done by disulfide bonds.
You need sulfhydryl groups, SH groups, for disulfide bond formation. This is present in cysteines. Now, is the disulfide bond a covalent bond or a non-covalent bond?
It's a
Covalent bond.
covalent bond.
Covalent bond. And does it depend on the environment? Does the formation of disulfide bond depend on the environment?
Sir, it happens because when somehow heat is given, these disulfide bonds get broken down, or it not very effective, that bonds.
Heat, you're saying, would break down disulfide bonds, is it?
Yes, sir.
Heat, temperature. Okay, I'm not sure about that, but what I know is there are specific chemicals that would change the environment around the disulfide bonds. We had also discussed about a couple of them earlier in our classes. Can anyone remember that?
Sir, that was beta mercaptanol, and another one is like DDT.
Yeah, it is DDT. Option A and B. These are the ones that would change the environment. So, does anyone know what exactly these two chemicals would do?
These are reducing agent.
So, what are reducing agents?
Sir, in this case, what that SS bond, the disulfide bond, is what they are doing, that they are reduced to the thiol groups, so that they are not going to bound somehow. But
Yeah, sorry.
sometimes it can be bounded. That somehow the affinity sometimes happens that it can bound. But the reducing agent's job is to break the disulfide and making it a thiol groups.
Right. So, whatever we have drawn here, does it depict what you're trying to say?
Yes, sir.
Okay. Now, this would happen in the presence of reducing agents. But one thing that we need to consider is this process also has directionality. It is not one directional, it is bidirectional. So, since these two molecules have specific half-life, meaning they would get degraded over time within solution. So what one should do is, whenever they are trying to do this, trying to break a disulfide bond by providing a reducing agent, they are just trying to alter the equilibrium more towards producing these sulfhydryl thiol groups rather than being present as a uh, a disulfide linkage. But this will not help in stopping the reformation of disulfide bonds. But rather, what would help stopping is attaching some molecule to this SH. Instead of H, if you replace it, there is a covalent linkage that would prevent formation of this disulfide bonds. Do you agree to that?
Yes, sir.
Yeah, so that is what this iodoacetamide does. It covalently modifies this sulfur's valency such that this SH is now present with an alkyl group. And this alkyl group and alkyl group being present between two sulfhydryl groups will not allow it to form a disulfide bond. Because if it has to form a disulfide bond, then this bond and this bond has to be broken, which cannot happen in the absence of an enzyme. So, that is how iodoacetamide. It's given as iodoacetate, but the right answer is iodoacetamide. That's how iodoacetamide helps in stopping the reformation of disulfide bonds. Was that clear? Was it clear that beta mercaptadgenol and DTT cannot always ensure that this disulfide bond is present as two sulfhydryl groups? Was that first clear?
Yes, sir.
Okay. The next question is, how many degrees of freedom does a diatomic molecule have? And four different options are given here: 4, 2, 6, and 3. Um, let's consider a diatomic molecule as oxygen. Oxygen has two bonds, it's a double bond, right? Now, how many degrees of freedom does this oxygen diatomic molecule have? Does anyone have an idea? Can anyone describe it?
Sir, if we are talking about the degree of freedom, um, it can actually two types of degree of freedom we are having. First is translational, and the one is rotational. So in translational, we can say that it can go to the x-axis also. It can go towards y-axis also. It can go towards z-axis also.
That gives us 3. Okay.
Yes, sir.
Okay. That is translational. Okay.
But sir, I'm not very clear about that how that rotational degrees it works here.
Okay. Can you think about vibration, or should we constrain only to rotation and translation?
Sir, it can in the sense we can consider that vibrational.
So they say that for a linear molecule, the rotational degree of freedom is 2, and there are 3n minus 5 degrees of vibrational freedom. So using that, we need to discuss this, and this is possible. This would reduce as the number of bonds are created. It would be different between C bond C, O double bond O. So one thing that you need to consider is, when you talk about the total degrees of freedom, it is 3 times n, which is 3 into 2 in this case. That would give you 6. And the rotational degrees of freedom is 2, and 3n minus 5 is the vibrational. But do you think diatomic molecules can have rotational or vibrational degrees of freedom?
So rotational is not that much prevalent. There is a restricted rotation because it's an if we talk about that oxygen molecule, it's in double bond. So there is a restricted rotation.
Rotation about what? Like, do we have an axis? Does it have an axis?
uh, should be having that particular axis of rotation.
So, how you can visualize this is you can consider three axes. Your molecule will be present in one axis, right? This is one O, this is another O. So, there are two axes that is perpendicular to these. So, it can rotate about these two axes. That way, it will have how many degrees of freedom, rotational degrees of freedom? We just drew that. How many do you think will it have now? If this is your double bond, so it will have with respect to this axis, and with respect to this axis it can rotate, so that has two rotational degrees of freedom, three translational degrees of freedom. It can move across all three axes. And this vibrational degree of freedom, it is present at higher temperatures only, not at all temperatures, which is why it has 6 degrees of freedom in total. Was that clear?
Sir, I can understand that there is a two rotational degree of freedom, but that vibrational degree I am not getting that.
So, what is the possible vibration do you think this molecule can have, Chandrama?
Sir, it could vibrate across the molecules means
So,
that O atom.
if it's vibrating, what would it mean? Whereas there is an electron cloud here and an electron cloud here. Now, both are same, both belong to the same, uh, how do I say, element, which means both have same electronegativity, which means both can pull the electrons with equal affinity. If one is pulling, the other would also try to pull. Does would that constitute a stretching vibration?
Yes, sir.
Yes, that is the vibrational degree of freedom that we observe. But when does this exist? Why is high temperature required? Only at higher temperatures, electrons get excited. And only if electrons get excited, they would try to move and your electron clouds would move. That is why at higher temperature, bonds are also broken. Is that trying to answer? I mean, did my answer help you?
Yes, sir.
Okay. The next question is the position for absorption band for carbonyl touching vibration has a frequency that is shown in vibrations per second. How do you convert this to this value? Does anyone have an idea about this? How do you convert frequency to wave number? Is there a relation between frequency and wave number?
Yes, sir. The frequency is equal to C by lambda, where the C is the light constant and the lambda is wavelength.
So if that's the case, how do we calculate here?
Sir, as the frequency is already given, so we can divide it by the speed of light, 3 into 10 to the power 8.
Okay, this is 10 to the power 13. It's typed as 10, 1013, it's 10 power 13. If that's the case, what would be the right answer?
Sir, it would be option A.
So you're
In
able to
approx.
approximately, right? It's 17, 3s are 51. It's simple as that. Right. So this was clear, right?
Yes, sir.
Okay. So the next question is, in an IR spectrum, which region corresponds to the fingerprint region? And four different wave number ranges are given. Before going to the right value, we can start with what a fingerprint region would mean. We can take a couple of minutes. So whoever wants to answer can first discuss what an IR spectrum is, then tell me what a fingerprint region is. Then we can go to the specific range. Okay? Yeah. Does anyone want to describe what the IR spectrum is? So IR, which stands for infrared, is present here, which is between microwave and visible light. It is that particular energy level. Now, what you need to know about this is that to compare molecules, there is this particular range between 600 and 1400 centimeter inverse. This is called as the fingerprint region. Now, this can be used to identify specific bonds, specific groups, specific chemistries, which would act like the fingerprint for a molecule, which is why it's called the fingerprint region. So the actual is 600 to 1400. The closest one that we have is 400 to 1500 centimeter inverse, which is the right answer here. Okay. The last question for today's class is, in an IR spectrum, a strong peak around 1600 centimeter inverse is indicative of dash. C double bond O stretching, CH stretching, NH bending, OH stretching. You can take a couple of minutes and then try to answer this question.
So will it be OH stretching due to O's electronegativity, high electronegativity?
So this is characteristic, but why do you think that particular value will be for OH stretching? Is there any particular reason? Yeah, Samiksha, you can unmute and try to justify.
So due to electronegativity, when light means infrared light will fall on that particular atom, then the peak will be means
No,
due
why
to its
specifically this
electronegativity.
answer is what I would want to know, because NH is there, CH is there. Is there any specific reason why you thought it would be OH stretching in this range?
So due to maybe due to the what that outer orbitals present in O, then the electrons will get to the excited state, and then the peak will get higher.
Maybe, but not at this particular thing. So each of these are characterized. We can't realistically change these unless you change the environment around them. Now you have this earth stitching. If there is a hydrogen bond with which is taking up this hydrogen, if there is some other electronegative atom which is taking up this, trying to pull this hydrogen towards it, forming a hydrogen bond, then maybe the value would be different. But all of these are characterized. So this is typically a memory question. So there is nothing specific to remember about this. These are a few values. You can just make a note of that here. I've included that in the presentation.
Okay,
And
sir.
one thing that you can notice is this NH bend from 1650 to 1580 centimeter inverse, that would correspond to NH bending. So that is why this value is specific to NH bending. All of these are characterized at isolation, so these would not vary. So you need not think of a particular value to correlate. If you want to remember, you can remember these, but try to understand how this bending or stretching would happen. That will be beneficial. Okay.
Okay, sir. Thank you, sir.
Right. So with this we come to end of today's class. If there are any questions, you can ask me. Otherwise, you can we can end the class.
Sir, I had a question means regarding not this topic, but due to my means regarding my further studies.
Uh,
I know, sir, that I'm not means very much punctual regarding your course, which you are taking. That means you are taking classes. I'm not punctual. I'm sorry for that. But sir, I had some doubts regarding means my further studies and all.
you can we can finish this call and then we can discuss that. If we'll just close the recording.
Okay, sir.